Yeah, but I don't know. It's like
We'll have a nice Thanksgiving, hopefully. How many people ate a lot of food? Not everybody, all right. How many people worked the entire weekend? Yeah, that's the problem with having a holiday in the middle of the semester. All right, hopefully you at least got 1 day breather before focus right back in on it. Today we're going to talk about thread level parallelism. In particular, we're going to remind you about parallel computing hardware very briefly. And then we're going to talk about consistency models for the memory systems when there are multiple threads. And finally, we're going to talk about programming using multiple threads on a single application to try to get performance improvements. And we'll use some very simple examples to show you some of the issues. Okay, so here's a picture of so here's a highlighted die. Here, the cartoon of that looks like this on the left. Every core has its own set of registers.
Professor.
Yeah.
Nothing.
Ah.
No.
Loose. All right. Hopefully this will not come loose again. All right. At least it wasn't a 25-minute Windows update. Okay. All right. So each core has its own L1 data cache, L1 instruction cache for instructions, and L2, and so forth. And they all share a last level cache on chip. And then there's main memory as well. Okay. We've also talked a little bit about what a out-of-order processor structure looks like. So here the notion is instead of executing the instructions one at a time, which would completely serialize things and you completely observe all the delays in certain instructions if you had slower instructions versus faster ones. Instead, you have a instruction cache that those instructions get decoded and then they get put in an operations queue. Okay. And this queue is fed into these function units as they become available. So in this particular case, we have 2 integer units, a floating point and a load store unit. The load store unit has access to the data cache. Okay, and so the overall performance is improved because potentially you can get all these function units operating in parallel. So maybe get a factor of 4 there. But also just the fact that if one thing is stalled, like suppose this you're stalled on a cache miss, you can be doing work on instructions that you normally think of as happening after the cache miss. Okay, and of course that only is possible because the hardware has to track all these dependencies and decide when 2 instructions in your serial sequence of code can indeed be take effect out of order, and when they can't. Okay. So hyperthreading is a particular form of parallelism. Typically on, say, an Intel processor, you have just 2-way hyperthreading, which is what's shown here. And here, what you have is basically 2 copies of this instruction control mechanism. So for A, you have its PC, program counter, you have its operation queue, and its register set. Okay, and similarly for B. So given what I said before about you've got all these function units that you can keep busy and so forth, why add the complication of hyperthreading on top of that? Why do we have hyperthreaded processors at all? Anybody know? It's like an example of when you might benefit from a hyperthreaded processor. Yes?
Well, I get you get to use the L1 and the L2 of 2 cores, maybe, and then
No, they actually share the L1 and L2.
Oh, okay.
Uh-huh. Yes.
Is it if one of the class S's hangs up on a really long instruction so that it can't think of anything else to do, like try and retrieve from the JSON?
Exactly. Exactly. So suppose, for instance, this guy is waiting on I/O, or takes a page fault, some operation that's going to take a very long time. There's just not enough things that in that one instruction stream that can be sort of pushed ahead and kept keeping things busy while you're waiting for that. And so you swap in a second one. Okay? And the hardware designers have discovered that, at least for most workloads, that there's diminishing returns. So basically 2 is a good amount, 3 is not that helpful, 4 is not that helpful, and so forth. Because you have to duplicate all the state, right? And so 2 is kind of the sweet spot for the last 15 years or so. All right? Good. Any questions on that? Okay, so our Shark machines are hyper-threaded. They have two-way hyper-threading. Okay, they have 8 cores each. They're fairly old machines at this point. You can get machines with many more cores than that. You can get machines with 72 cores, for instance. Those tend to be more for servers than for use as client devices. So as mentioned, what we're going to talk about today is, in the context of a single program, trying to get improved speed up by using multiple cores. So it's sort of truly parallel processing within a single program. Okay, and what we're going to talk about today is that there are things you can do when you write your program to make this work better, right? To actually achieve some of the possible speed ups you might be able to get. I mean, ideally, for instance, on your Shark machines, because you have 8 cores and each have two-way hyperthreading, theoretically, at least, you might be able to get a speed up of 16x over just over single thread execution. Okay, by executing 16 threads at once, and if they're all able to keep busy, that's theoretically possible. Although, because of various overheads, you never exactly achieve that benefit. Okay, but you can get close with things that are what's called highly parallel. Not a lot of coordination between the tasks. Okay, so given that we have these different threads and they're all accessing the same main memory, right, they're all within the same address space. Okay, there's a notion of memory consistency. So if I have multiple threads and they're each updating memory, okay, and they're each reading memory, then if there was no coordination going on, there would be it'd be a jumbled mess, right? You wouldn't know what to expect when you read something that someone else has written, and so forth. And so to create some structure over this mess that people can reason about when they write programs, there's notions of memory consistency models. Okay, it's sort of abstract model of how the hardware handles concurrent access. It's sort of you can think of it as the contract, the API, the contract between software and hardware. If the software writes assuming that this is the memory consistency model, the hardware is guaranteed to support that. Okay, so what are some of the things that could go wrong? Suppose that we had not caches that weren't kept at all, what's called coherent, where they're sort of kept in sync. Okay, this may happen, for instance, if these are not like a cache on one of the Shark machines, but maybe scratched memory on a GPU. Okay, where there's no coherence. So what can happen there is that if main memory starts off with A equals 1 and B equals 100, and then thread 1 has these instructions to execute, and thread 2 has these instructions to execute, then one possible thing that can happen is that this instruction happens to happen first, and so this thread pulls into its cache the cache line that contains the value A, and updates the value of A to 2. Okay, so from this perspective, this cache A is still 2, is now 2. And then B can come along and do the same thing for B and set it to 200. Now, over here, thread 2 now wants to print A. Okay? Well, it doesn't, if these aren't kept, if there's no coordination between these caches, it has no idea that A has been updated over here. So it just goes and readily grabs what's really a stale value, an old value, from main memory and brings that into its cache. And so when it goes to print A, it will print 1. And likewise, thread 1 can do the same thing. It doesn't know anything about, if there's no coordination between these caches, it doesn't know anything about the fact that B has been updated, that this value is stale, and so it reads in the old value and prints that out. Okay? Any questions on that? Yes?
Could this be prevented using the read-write lock that we've been talking about?
If you, well, notice that these are two different, okay, so you have the separate thing going on in A and B. So if you had A and you grabbed, if this thread grabbed a lock before it updated it, then yes, this thread would actually not be able to pull this into its cache because it would be locked out until this thread was done, okay? Now, the trick though is that when this thread unlocked it, it's going to have to, before it does that, make sure it gets pushed back out to memory so that when this guy is able to get the lock, it actually gets the fresh value, not the stale value. Okay, good. Okay, and at some later point in the scenario we've been going through here, it's true that these are write-back caches, so at some later point, this A2 will get pushed out to memory, and this B200 will get pushed out to memory. But there was nothing that made it pushed out in time to make these print statements make sense. Okay, so so one of the first things that you might want out of a memory consistency model is that from the standpoint of a thread, its operations appear to happen in order. Okay, so that's what's mean these thread consistency constraints, that the write of A should somehow take effect before the read of B, and similarly here the write of B should take effect before the read of A. Okay. Good. So sequential consistency is the most popular, convenient model for memory consistency because it has a very simple way of reasoning about it as a programmer. The way you reason about it is that memory behaves as if only one operation occurred at a time. Okay, even though there's a lot of parallelism, for correctness, only one operation appeared at a time. And that has to be in order that's consistent with the order of operations in each thread, right? Consistent with these things here. Okay? But otherwise, you know, given that thread 1s have to be in order and thread 2s have to be in order, the shuffling of the deck can be any which way, right? There's no restrictions on how those can be shuffled. So what this shows here for this exact same program is all the possible combinations of things that can happen, right? So because of the, of these four operations, because of the thread consistency ordering, the ones that have to take effect first is the first ones of each thread, okay? One or the other one of those. So we have those two cases there. Let's suppose that the write of A was the first one to take effect, okay? That means that next, still the write of B can go, and the read of B can go, but still not the read of A because it's blocked by the write of B, okay, in this memory consistent model. Not in the real hardware, but in the memory consistent model, okay? So that means there's only two choices. The next thing can happen is either this read of B or the write of B. So if it's the read of B, well, then you're basically done because thread 1's done its two operations. So the only thing that can happen the rest of the way is thread 2 gets its two operations done. Okay? So if that's what happens, if this is the order in which conceptually things happen, what gets printed? It is, yeah.
102.
Yep. Okay, do you see why? because when this guy did the read of B, it read this value here because the write hasn't occurred yet. When this guy did the read of A, over here, this write of A had already occurred. That's why I get the 2. Okay, what about the next one? Write A, write B, read A. Any ideas there? Anybody else? Okay. Yeah. Yeah. Good. You see why? Because both writes were done, so you're going to get before any of the readings, so you're going to get the 2 values written. Okay, and so forth. You can do that same, test yourself on the same, all the different combinations. So then the question is, what combinations weren't possible under sequential consistency? What's something that could not be printed? Yes.
101.
Okay, why not?
Because write A or write B is going to happen first, no matter what, before the read A or read B.
That's right. You can't get, in order, you can't get to sort of both these reads without, or at least one, these reads without touching at least one write. So before the first read occurs, at least one of the writes have to occur, and therefore you can't get the old values for both things. And that's why you don't see here any combination where that's what plays out. Okay. Any questions so far? Yes?
I thought that when you have 2 threads, they both act as if they're behaving separately.
So the memory consistency model is sort of the contract, the promise from the hardware that there will be some restrictions on what the state of memory can be. Okay, and in particular, sequential. So you're right in the sense that there's our first example. This one here, basically any combination was possible because there was no coordination in the memory. There was no memory consistency. So they could behave independently. They could print out whatever. In fact, here they did print out that illegal value in sequential consistency. All bets are off. But when we impose the sequential consistency abstraction, then there's some promise by hardware that, and mechanisms in place to ensure this, that that won't happen. Okay, does that make sense?
I guess what I'm asking is that, so when you, as the same thread that you get when you fork, right?
Yeah.
Yeah, so shouldn't it be that if you're like, let's say thread 2, it just always takes the A from before the thread, not possibly the A from thread 1?
So this is like p-threads create. So you're creating 2 threads within the same address space. Okay, and so they actually they're sharing the same memory. Okay, it's not the case with of like an entire process fork where it's a separate memory with, it behaves like a separate memory with copy on write and things like that. Yeah, sorry, I should have made that clearer. Okay, good. All right, so this is the, yeah, before this is not sequential consistency because that's not possible under the rules of sequential consistency. Okay, so, but that was because there was no coordination between the caches. But another thing that can happen is even if the caches themselves are coordinated, because of the out of order execution at the processor, things can sort of get reversed by the time that the loads and stores even occur. The memory system even observes it. So here's an example where what happens is that thread 2 has this pool, this queue of instructions, this pool of instructions it's trying to execute, and it includes both these 2 instructions. Okay, and it goes to it has the different functional units, and it so happens that this one is the one that happens first. Okay, so therefore you print 1 because that's the current value of A. That's the value of A. And then similarly on this side, you could have this one go first. Okay, and then later these writes to A and write to B occur. Okay, So although we use the example of caches not talking to each other, the problem of supporting sequential consistency is one that involves more than just caches talking to each other, right? It involves the processor realizing, the out-of-order execution of the processor realizing it can't swap these around if it wants to maintain sequential consistency, okay? All right. Now, so the dirty secret is that while everybody, programmers and software and things like that, want to have sequential consistency, it's there's a heavy performance penalty to be paid typically in order to have a machine, a processor that supports sequential consistency. So instead, what you get on Intel processors and others, including those from, say, Sun and Oracle, are memory consistency models that are weaker than sequential consistency. Okay, and operations such as fence operations that allow you to enforce an ordering between two instructions. So the notion is that the processor actually, because of its out-of-order execution, could give you this, and that's bad. That's not what you expected. So what you have to do is you have to put in between these two, on both sides, one of these, a particular type of fence operation, S fence. And that will tell the hardware, the out-of-order execution, that the order of these two things actually matters, and therefore I better do this one first before I do this one, and I better do this one first before I do this one. Okay? So in a perfect world, the hardware would just provide sequential consistency. It would be fast, and you wouldn't have to ever add your own, these silly fence operations in there. But unfortunately, that's not the world we live in, because people didn't want to give up the performance that would be required to give up in order to get that perfect world in terms of modeling. And so instead, we have this imperfect world where we have to put in fence operations if we want to ensure particular things order. All right. So, but there are ways in which the processor does help. Okay, so the processor does not allow for non-coherence in caches. Okay, and there's a number of ways in which is done. This was historically the first was known as Snoopy caching. Snoopy caches has nothing to do with Charlie Brown and Peanuts. It has to do with the fact that there's this bus. Remember, there's a shared bus that connects the memory system to caches, and you have the cache controllers snoop. You pay attention to what's on the bus, even when things that they don't request are going by. All right, so how does that work here? So what we have is a tag. You're familiar with certain kinds of tags in your cache lab, right? This is one in particular for shared memory settings. An exclusive tag means that you've gotten permission to write, that you have a writable copy of that cache line in your cache. Okay. So the first thing that happens when thread 1 tries to do this write is that it first grabs the cache line in exclusive mode, and then it does the write. Okay. And similarly for thread 2, grabs cache line that contains B in exclusive mode and does the write. Now, when you go to do one of these reads in order to do the print, what happens is that the request goes out, say for A, say over here, the request goes out for A. Wrong way, there we go. And what happens is that you put the request here on the bus, say, I'd like to read A. This cache controller is snooping on that bus and says, oh, I have the latest copy of A. Here, let me have it. Let me supply it for you. So you supply the value from the cache. And then because this is no longer the exclusive copy of this cache, you change the state to shared. Okay. So this guy now has a shared copy, and this guy also has a shared copy. Okay, so you set the tag to shared. Okay, and notice that we did that based on snooping off this bus here, and in particular, we knew this guy replied, we knew not to use this value here, that this was a stale value in memory, and that the place to get the latest value of A was the cache line. Right? And this generalizes to any number of caches and threads, right? You could have 32 of these, and similar things happen. When it's exclusive mode, there can be only one copy in one cache. When it's shared mode, there can be as many copies as you like. Okay, and similarly, in order to print B, you first put the request for B on the bus. This cache controller sees that, says, oh, I have the latest copy of B. I'm going to change it from exclusive to shared and pass it to you, and now it's shared in both places. Yes?
Wait, so when thread 2 decides to look for A, why does it go to the thread 1's cache, not its own cache?
So here, you're right. It would first look at its own cache, and it would be a miss. A is not here. So before, what happened is it went to the main memory and got the stale value. Now with Snoopy caching, which is a way of coordinating the caches and keeping them consistent, when this request for A goes out on the bus, this guy doesn't reply, this guy does. And that's how you get the most recent value. So thread 2 has no idea where A is. He doesn't know if it's in main memory, he doesn't know if it's in some other cache somewhere else in the system. Doesn't matter because of the snooping protocol, all the cache controllers are watching what the requests are. And so when a request for A goes out on the bus, then anybody who has A can respond. In particular, this guy has to respond because he has the exclusive copy of A. Okay. Any other questions? Yes.
So in what kind of situation would the value of A come from main memory instead of thread 1? Would it be that, so like, could thread 1 have the value of A, but at the same time it doesn't supply the value of A? So it doesn't have the tag or something?
So it's always safe for the cache to respond, right?
Because it seems like
Because any cache has a more value at least as fresh as what's in main memory. Okay, because these are write back caches. Now, the case where memory supplies the value is like if this was evicted, right?
so the cache doesn't have.
So no cache has the value, then you supply it from memory.
Oh, but then the only difference seems to be that you don't really get the value from main memory if there is a value attached, right? So like, why do we have to have that tag?
Because it was important that we got 2 and not 1.
Okay.
We wanted the recent value, not the stale one.
Oh, okay.
And when another important point is when the last copy of this A gets evicted, then you have to write back to update the memory to B2, right? So that you don't lose track of the real value.
Oh, okay.
All right, good. Okay, so to ensure sequential consistency, we need both sort of the proper cache and memory behavior and also inter-thread ordering constraints, sometimes by inserting the fence operations. Okay. So for thread level parallelism, we're going to do a simple example. Okay. In this example, we want to sum the numbers between 0 and n minus 1. And we're going to do that by partitioning the numbers into k ranges of this many values each. And then each of however many threads we have, say k threads, will process one range. And then there's going to be, it doesn't divide evenly necessarily. So there's going to be some leftover at the end of this range. And we're just going to accumulate that serially because it's not going to be that much if n is large enough. And the first thing we're going to try is method 1, which is that all the threads update a single global variable. okay, the running sum. And we're going to have three ways of doing that. One is without synchronization. One is we're going to use our pthread semaphore. And one we're going to use our pthread mutex, which is a semaphore where the values are just 0 or 1. Okay. So again, single global variable. Here it is. Okay, global sum. Here's our a semaphore and a mutex. We're going to use one or the other. The number of elements that are summed by each thread is stored there. Thread IDs are stored, and identifying each thread. Okay. Okay, so the number of elements per thread, as we said, it was just the total number of elements divided by the number of threads, and it automatically gets rounded down. Things start at 0. We're going to create all the threads one at a time, right? So we let the ith thread know that it's the ID I, and then we pass that as an argument. And the threads go off and run, and then eventually when all things are done, we have this join. We place the result in a local variable, and then we finish up. So we say that if each thread did elements times number of threads, then number of elements per thread times number of threads is how many that they did. Got done in all. So we start there, and we finish off the rest of the list one at a time. And because again we're just adding up the actual numbers themselves, it's just a summing of E, right? So it's n minus 2, n minus 1, done. Okay. All right. So here's what each of the threads. Right. So they compute. So we've got this whole range of numbers, right, from 0 to n minus 1. And we're chunking it, right? So you just compute where you start. So you start at my_d times number of elements per thread. So the first one starts at 0. The second one starts at number of elements per thread, and so forth. Right, elements per thread, and so forth. And then you end at that many elements later, right? So that's your range. And so you're just going to loop between the start and the end one at a time and accumulate to this global variable that's with no synchronization. Okay? So how does that perform? Well, here's the number of threads we run it on, starting with 1. Okay? On a single thread, this thing took 2.5 seconds, roughly. We ran n equals 2 to the 30th. And it got better for a while, up until around, I don't know, maybe 8 threads or so, maybe slight better after that. But this, and the best speed up overall was 2.86, okay? But it got the wrong answer. Why is that? Anybody else?
Because it's got the same race conditions as we saw earlier with multiple threads and update on the value.
Right. Basically what's happening here, right, is you're reading, even though it's a single instruction here, you're reading global sum, you're adding I, and you're writing back out global sum. And in between, if somebody else reads it and does the same thing, then you miss entire values. Okay. All right, so let's try putting a semaphore around this. Okay, so at least this becomes atomic, right? Basically, no one else can, when I'm updating, adding I to the global sum, no one else is updating global sum at the same time. Alternatively, we can use the mutex, right? Just the binary version of the semaphore. And when we do that, we see that, so this was the one with the races. It's now sort of almost hugging 0 relative to the others. Time, elapsed seconds here. We see that the semaphore is horrendous, and the mutex is also really bad. Okay? We went from 2.5 seconds to around 10 minutes. Okay? So that's clearly not what we want to do. Okay? So why the poor performance? Well, there's a lot of overheads in these, both mutex and semaphores, and you put them inside this tight loop. Things go slow down. Okay. So separate accumulation, it's a natural thing to try. We're going to show you 3 methods of that. Accumulating contiguous array elements, accumulating spaced apart array elements, and accumulated registers. Okay. So again, we have this partial sum, and we have this parameter called spacing. Okay. All right. So as before, we divide the number of elements evenly by the number of threads. We go ahead and set the partial sum, which is now on a per thread basis, to be 0. So when spacing equals 1, this is just, p sum of 0, p sum of 1, p sum of 2, p sum of 3, and so forth, kind of what you'd expect. But we'll see in a minute why having spacing there helps. We have p thread create as before. Join result, we have sort of add up the partial sum. So each of the threads has computed a local partial sum of the stuff in its elements, and we just want to serially run through those and add them all up. Okay, and that just gets us through the ones that divide evenly. We still have the same serial loop at the end for the leftovers for the things when they don't divide evenly. Okay, so what is each thread's code looks like? Again, it computes a start and an end, and then has the notion of index that, again, when spacing is 1, is kind of what you were expecting before. And it just goes through and it runs through its list and it adds up, does all the sums, but it does it on a on something where its own index. So it's accumulating in a part of a p sum array that no other thread ID, no other thread is also computing in. Okay. So when you do that, so here's the one we showed with arrays. Okay, that was the serial global counter and it got the incorrect answer. If spacing was 1, we get this green curve. So we actually have some improvement by doing the partial sum. Plus we have the correct answer. Always good to get the correct answer. And then if we set spacing to something other than 1, which we'll talk about in a minute, we get even better results. Okay, so in terms of the spacing equals 1 case, we get a 5x speed up, and the spaced apart speed up, we can get up to 13x. Okay, so significant difference. All right. So before I get to that, I want to ask about mutexes. So why didn't I need a mutex for this? Yes.
Because all the threads are independent.
In what sense?
In the sense that there's no worry that they're going to influence each other. They're each given their own separate little space to work in. And
That's right.
So since they aren't influencing each other, you don't need to worry about what order they execute.
Yep. There's no data race at all here, right? They're all operating on separate accumulators, right? Separate parts of the p sum array. Okay. So so we had this notion that when we had spacing equals 1, we got this green curve. When we have spacing greater than 1, a particular value greater than 1, we got a better curve. So the question is why? Yes?
Because whenever they're close together, then they can all get cached by the different, by each thread's cache, and then that's do they slow it down? So
They
put it to multiple caches, basically.
that's I mean you're on the right track. I'm not saying the right word yet.
So they get put into cache, and then each cache has to compete for which one is maintaining the most recently updated version of the whole memory block.
But why do they? Why? I mean, they're two separate accumulators. Why do they get placed in the same cache?
With spatial locality of memory.
Because they get placed in the same cache line, right? That was the word, line. Okay. So here's a picture that looks like that, right? That if you have the 8-byte accumulation that sorry, this is the p-sum array. Okay, so here's the different 0, 7, 8, 15. But if within the same cache line, you could fit 8 of these sums, right? Then all these 8 will, want to all update the same cache line. So the cache line will, thread ID 0 will grab the cache line in exclusive mode and do an update. And then thread ID, another one, maybe 7, will say, well, I need to update that cache line too. So it will grab that, invalidate the other cache line, grab an exclusive copy of that, and so forth. And go back and forth, back and forth, back and forth. Okay? And you can do experiments where you see just how much ping-ponging happens in this case. But it does result in a lot of overhead. Okay. So yeah, threads sharing common cache block will keep fighting each other for access to the block. Okay. So that's called fault sharing. So ideally, though, of course, is that you want to have one of these accumulators per cache line, the cache block. So if 0 gets here, then the next counter you'd want to put here. Okay. And the way we do that is through the spacing parameter. So if spacing parameter is set to be 8, then if you look back at the code, everything sort of jumps 8 apart, right? And then every accumulated counter gets its own cache line. Okay. And then you can see that from here. This is showing again the spacing use 1 curve. As you space things further apart, you get fewer and fewer things competing for the same cache lines. But it's only when you get to the 8 case that you get, it's kind of hidden under this other curve, but you get the curve that runs here. Okay, you get the best performance. If you were to make spacing even bigger than 8, like 16, it's no better. The 16 curve is right on top of the 8 curve. Okay? So no benefit increasing spacing beyond 8, but 8-byte values in a 64-byte cache line, you can get 8 of them in there, and so if you jump space by 8, you jump over. Any questions? Yeah.
Oh, so like the spacing doesn't change anything regarding like cache hits and misses. It's just about like using more of the cache, like because like they can't like two threads can't access the same line at the same time.
Yeah. So we think of that so in cache lectures, when we just had a single thread, we talked about cold misses and conflict misses and capacity misses. There's also a type of miss in this shared environment that's called a coherence miss. Okay, so these are misses. When they are fighting with each other to access the block, they are suffering a miss. Right? So the first one brings it into its cache, and it gets evicted from the other guy's cache. So it's over here. So when this guy wants to read it, it's a miss, and it's got to get it, and it brings it over here. In the meantime, it invalidates this one, because this is the exclusive copy, and so then this guy suffers a miss. So it actually is accumulating tons and tons of misses. There's this kind of miss called a coherence miss, because it's part of the cache coherence protocol. Good. Other questions? Yes?
So if you have 2 threads and they both call malloc fairly shortly after each other, is there a chance that they're both malloc, like given regions of memory that are within the same cache line?
Usually malloc is padded out, right? I mean, I think that has to do with that's a danger, but usually a good implementation malloc will avoid that by padding. Right?
Okay, so we'll actually pad the entire cache line out.
Yeah.
Okay, and for the Snoopy caches, if you have a 3rd thread, so if you have like one of the threads gets exclusive access to something, and then the 2nd thread requests that same piece of memory, so now it's shared memory.
Yep.
Then the 3rd thread comes along and requests that same piece of memory, because whenever it requests it, none of the caches see like it's not in exclusive mode, like it's not
Yep.
marked as exclusive.
Yep.
So won't you end up getting the like old version of memory that doesn't have the latest updates?
No, if you have if a cache has a shared version of it, it should respond as well.
Okay, how does it respond? Does it also give the shared, does it also just give the shared version of it?
Yeah.
as?
Yeah.
Okay.
Yeah, good. Okay, and the third version we're going to look at is register accumulation. So here, instead of having them bother to write to shared memory at all, they accumulate in a local variable, which the compiler will stick in a register. And so all the summing gets done without worrying about memory at all. And then only at the end do you write out the partial sum into shared memory so that the main thread can then go through and add all those up. And you get better performance still, right? You get this green line. Okay, so red was the best from the previous graphs, and now we get green. So the total speed up is 7.5. It's basically 2x faster than the fastest memory accumulation version, which is this red curve. One of the things that this sort of says, beware the speed up metric. So I think, I can't remember if we've talked about this before, but sort of a lazy practice would be to say, I run my parallel code on one thread, and I see where that lands, and then I measure the performance improvement from there, and call that my speed up. So if this is like the fastest thing here, then I call that my speed up. But if it turns out that running the whole darn thing sequentially would be a lot faster than what you started at, that's really an unfair comparison. So a much better comparison is to look at the fastest you can version of the code you can write sequentially, and wherever that hits on this time chart, right? And then see how much you can speed up over that. And what often happens is that it takes, maybe the one thread parallel version, the two thread parallel version, the three thread parallel version, four thread parallel version. All of them are slower than the serial version, right? Because of overheads of what you had to do to get them correct in parallel context. And it's only when you get up to maybe 8 threads or 16 threads or whatever that you start to see some benefit of parallelism. Okay, any questions on that? Okay, so shared memory sharing memory can be expensive. You want to pay attention to true sharing, which is when they're both accessing the same actual bytes. Pay attention to false sharing. It's in the same cache line, but different bytes. Use registers whenever possible. Use your local cache. Try to get cache hits whenever possible. Things don't divide out evenly. Deal with the leftovers. And when examining performance, compare to the best possible sequential implementation, not just how much faster your own code runs relative to your own parallel code runs relative to itself. Okay, questions so far? All right, quiz. All right, let's see how people did. No one got 100%, which made me believe I got something wrong in my answer key. All right, so, okay, so we have these two threads. We have sequential consistency, right? And okay, so what orderings are possible? So initially 0 and 2. So okay, so is it possible to get 0 and 2? Yes, if this thread, if these are the first two things that execute, you get 0 and 2. Is it possible to get 0 and 3? If this executes first, then these two, and then that one, you get 0 and 3. Is it possible to get 1 and 2? So if this goes first, and then that gets you 1. That's B. Okay, and is it possible that's maybe where the mistake is? Okay. 1 and 2. Okay. Oh, I see what you're doing. Sorry. Okay, good. See, that's why no one was getting right. I messed up the question. I meant to reverse these two. Make it more interesting. Okay. There was meant to be, if I was having all sorts of trouble with the formatting of this. It looks nice now, but it took me like, and I kept having to retype this. I think one of the times I retyped it, I swapped the order, what I was intending. It was intended to be that similar to the example we showed in class, that if you printed, if these were two reversed, if you printed B equals 3, then you knew that A equals 1 already, so you couldn't also print A equals 0. So but the way I wrote that problem up, they're all possible. So the problem was silly. Okay. But anyway, you get the idea. Okay, that there's certain combinations of things that aren't possible when you insist upon sequential consistency. All right, good. Let's see, how do I get this to do? Hello. Okay. All right, so how do we do on this? Okay, so the trick here was that we wanted true sharing. Okay. And so in order to avoid true sharing, all you needed was that each thread had its own part of the partial array, right? So spacing was 1 suffice to stop them from sort of trampling on top of each other, right? So that's why the answer here is 1. And all right, people got this one, good. So for fault sharing, in order to get them to be in separate cache lines, you need to have spacing be C over T. And the only tricky part was asking you whether to round up or round down. You need to round up because you need to make sure you're sort of fresh passed into the next cache line. So you need to take this basically the ceiling of C over T.
Professor?
Yes?
Just to make sure I understand here, so it's saying the minimum value to avoid false sharing. So that would still be C over T rounded up? Wouldn't that be to achieve false sharing?
If I round up, that means I've spaced them far apart, that they're not sharing cache lines. And therefore, there's no false sharing.
Oh, yeah, okay.
All right, other questions on the quiz? I knew something was suspicious when no one's getting 100%. Okay. Good. Okay, so let's take the rest of the class to look at a more substantial example, sorting. It turns out there's lots of ways to sort, lots of proposed methods for sorting efficiently on parallel machines in multi-threaded, on multiple cores. we're going to look at variants of quicksort. So let's remind you of how quicksort works serially. You have a set of values. You choose a pivot from that value according to some rule of pivots, and you rearrange such that all the values, L is the set of all values less than or equal to the pivot, R is the set of values greater than or equal to the pivot, recursively sort L, recursively sort R, and return the concatenation. So it looks like this. You start with X, you pick a pivot, you divide things into all the things less than, all the things in X that are less than this P, all the things that are greater than the P, and now you pick a pivot for this side and repeat over here until recursion and so forth, until eventually that entire side gets sorted. Then you pick a pivot for the right side, and you go until all those things are sorted, and then the final result looks like that. Okay? So you can see why this has a feel for why it might be a nice thing to try to parallelize, because once you've got this thing divided into a left side and a right side, there's no interaction anymore between those two sides. So you might as well do those two halves in parallel. Okay? And so that's what we will do. Okay, so first, this is just the code. If the number of elements we're trying to sort is at most 1, nothing to be done. If it's exactly 2, then if they're out of order, you swap them. Otherwise, you're going to partition it and return M, which is sort of the position in this list of where the partition falls. So if M is 1, that means you picked out a very unlucky partition. Everything in that part of the array is bigger than M, and so there was bigger than the pivot, and so there was nothing to be done. But the normal case is that M is bigger than 1, and so you sort on that left half, and then similarly you check for the extreme where the item you picked as a pivot happened to be the greatest item there was nothing to be done to the right of it, but in the typical case there is something to be done to the right of it, and you go ahead and do that serially. Right, so recursively sort L or R if it has more than one element. Okay, so let's look at the parallel version visually. Right, we start as before. We do this, and the only difference now is that we pick both these pivots at the same time, right? And do those in parallel. When we do, in parallel, we get these pieces like this. Now we have 4 pieces, and we recurse on those in parallel, and so forth, until eventually all that parallel recursion stops, and we produce the sorted version of these two halves, and then we're done. Okay. So if you look at the thread structure, each of these sorting tasks has some range of the array X, right? And it's doing its thing inside there. I'm going to run this as a separate thread. Now, when these, so it turns out, like I said, there's a lot of overhead in doing things in parallel. So well-known for decades is that when you reach a certain problem size, a subproblem size that's sufficiently small, you might as well just do the serial code. Okay, and so when we get subranges that are sufficiently small, we'll use our fast serial quicksort to finish it up. Okay, but if you have a piece that's large, you're going to partition the subrange and spawn 2 tasks to deal with the left and right side. Okay, so you have this task to spawn 2 tasks, and this one takes the left, and this one takes the right, and so forth. Okay. Sort of the simplified top-level code. Right, you just compute your base. There's a base and end. There's a task queue. We have this helper routine that we're going to call. So we set up the data structures, call a recursive sort routine, keep joining threads until they're done, and then free the data structures. So what does this look like? The helper thread, what it does is that if the the number of elements is smaller than this threshold, and the threshold we're going to use to switch to serial code, then we go ahead and sort serially. Otherwise, we're going to create this new task and ask it to sort half of it, okay? So large partition will spawn new sort task. Okay, the sort thread is going to, again, call this partition routine that picks this M. And again, if either side is greater than 1 in its size, it's going to call the helper routine to recursively sort that part as well. Okay, so you get the task parameters, you perform the partitioning step, you call recursive sort on each partition. All right, so how does it do? Okay. So our parallel quicksort, we're sorting 2 to 37th random values in this particular case. And what we're plotting here is where our cutoff is. Right? What fraction of the input do we decide that now's the time to transition to serial sort? Okay. So if 1 means we do serial the whole way, so that's way up here. Okay. And so forth. As we go further along this curve, we basically, somewhere in here, I guess, reach a sweet spot. Somewhere in here, not clear exactly where the lowest spot is. But what that says is that when this much of you have a subproblem of this size, then you are going to switch to the serial thing. Okay, but you don't want to do that too soon because then the thing starts slowing up again, right? If you jump too soon to doing it serially, you've missed out on some potential speed up that you get from the parallel version. And the best speed up that you get in the end is 6.84, even though you potentially could have, you're running on 8 cores, each of which is hypothetical, so you could potentially get, so this is the potential, the 8 core. Let's just say if you just do a straight line here, if you just got factor of 8 speed up, you'd get there. There's two-way hyperthreading, so you could get up to a factor of 16 speed up, you get there. Okay. So what this is showing is that even with the best choice for when to switch to the serial version, there's still some gap here. Right? You're not getting the perfect linear speed up. Okay. Any ideas why? Is there still any part of this code that's actually, I guess you can't tell because I didn't really show you inside the box. Well, it turns out that one of the reasons this isn't doing perfect speed up is that partition routine, where you, given a pivot, you scan through the elements and you accumulate all the ones that are less than over here and all the ones that are right than over here, so that you can hand off a less than equal pivot right then. That was done serially in this code. Okay, and because of that, the overall best speed up you could obtain was limited. And the way we think about that is something that's known as Amdahl's law. So if you have a problem where there's amount t, total sequential time required, and you say, oh, of that total, I'm actually able to speed up some fraction p of it, between 0 and 1. Okay? And of that amount of that work, I actually get a speed up factor of k. Okay, so if I ran on 8 cores and I got perfect speed up, then k would be 8. If I ran on 8 cores, but I only got a factor of 6 speed up, then k would be 6. Then the thing to observe is that the resulting performance is, well, on the part that you are able to speed up, right, which is the fraction of the work p times t that is amenable to speed up, you get your nice factor of k speed up. So it runs k times faster. But there's still this remaining part that ran serially, right? This 1 minus p fraction of the total that ran serially. So and this can be the bottleneck. And that's the Amdahl's law is this formula. So even if you could get infinite speed up, k equals infinity, on the part of the code that you can speed up, then that all it best it does is that drops it to 0, and your time is still 1 minus p times t, okay, which may not have been what you were hoping for. So here's an example. Suppose I say, okay, I'm able to speed up 90% of my code, okay? And not only that, I can speed it up by a factor of 9. So that seems like overall I ought to be speeding up the whole thing by, I don't know, maybe 80% or something, you know? But no, because of Amdahl's law, yes, on that 90%, you get a speed up of 9, but on that 10%, you're stuck running serially slow. So, you know, it takes one time unit to run the parallel part, one time unit to run the sequential part, and so the end result is 2. So you only sped up by a factor of 5. You lost almost half your speed up because of that 10% of things you couldn't speed up. And in fact, the maximum possible speed up in this case is 1. Okay. All right. So in terms of parallel quicksort, that partitioning at the top level, I picked that first pivot. The code just ran through serially, right? So there was no speed up in that top partition, okay, in the partitions part. The second level, I already got it split into two pieces, right? So they're on expectation at least, they're half the size each, and so I can get potentially 2x speed up, and similarly 4x speed up, 8x, and so forth. Things go down, and so and the kth level, I can get up to 2 to the k minus 1x speed up. But you know that top level is gonna still kill me, right? Okay, and so in order, if you really wanted to get better results or have this speed up on larger machines and so forth, you're going to need to parallelize the partitioning step. Okay, and there are ways to do that that are both look kind of like quicksort. And like I said, there's other ways of sorting. So one common way would be to just grab at random a whole bunch of pivots, okay, and then sort those pivots, and then now those create bucket boundaries for the rest of the arrays, and then you just go through and you take each core can take a chunk of those other values and say, oh, okay, this value falls between these two pivot points. I'll stick it there, and so forth. And so you just fill up all these buckets, and then you're end up with a situation where you've got this array and all your little pivots that you've all now done in parallel, and then you just have to, and then all the things in this bucket fall between these two pivots, so you just have to recurse on these things, okay? And sometimes these things are already small enough that you can just do something serially at that point. Okay. Okay, I've forgotten I had this animation here. So there's parallelizing the partition step. One way to do that is, so another way to do that, which is more like quicksort, is you pick a single pivot, but you just have them each create their own little splits between these, right? So this thread just splits up L4 and R4, and then you collapse them together, concatenate them together, so that all the L's are first, and then all the R's are second. Okay. Okay. But on the Shark machines, at least, and the size of problems that we were running, the parallel partitioning didn't really help much. And so that's why we showed you the simpler results. Okay, but smarter algorithms, other machine contexts, parallel partitioning, or there's other styles of running sorting in parallel can be very effective, and you can get speed ups of 60 on these 72 core machines and stuff sorted. So it's definitely doable to get really nice speed ups in parallel sorting. Okay, so lessons learned: we must have a parallelization strategy. Things like find some independent work for the processor to do. Use divide and conquer. we saw that once we put in semaphores or mutexes in inner loops, that was extremely expensive, so we want to try to avoid those. We want to understand things like fault sharing and truth sharing and races and things like that. And part of that is you need to understand how the caches are laid out, which you guys know from doing all your cache lab stuff. Amdahl's law can be a killer. Make sure that you think about how much of the overall code you're able to speed up before you get overly optimistic about how much benefit your parallel is going to get. But this is the world we live in, right? With lots of cores, and they can be very useful for speeding up programs, and particularly it's pretty easy to get modest levels of parallelism. And you could test out multiple strategies, and just like test out multiple strategies for your malloc lab, and find out which ones actually achieve the best performance. Okay, any questions on that? Okay, so that's it. Next time we'll talk about the future of computing.